Hello and welcome to this astronomy homework help video where we're going to talk about the inverse square law of light intensity and how to calculate apparent magnitude. I'm not going to get into the theory of the ideas here, but you are welcome to look at the background reading as you can see in this document that I have open. And one thing that we're going to be referring to is going to be this formula right here. This will come up quite a bit, as will one other formula, which is the inverse square law itself. This is the apparent magnitude formula. And we're also actually going to be referring to this diagram here. Think of it as a table of values, but presented as a number line. These include the apparent magnitude of objects in the sky, such as the sun, the full moon, and so on. So those are some numbers we're going to be referring to. Again, leave the theory to background reading. All right, so let's go ahead and look at the different parts of the problem, and I'll give you an idea of what to expect in the remaining minutes of the video. Well, I'm going to go through the key ideas and setup of parts A, B, C, D, and E, which are all 5 parts of the problem. And after I'm done with that, I'm going to revisit A and D to do a extended numerical example with some values that aren't the ones that you're asked to work with. So let's go ahead and take a look at part A. All right, so in part A, our key idea is that we want to work with the apparent magnitude formula. All right, so we're going to work with the formula that is written as m2 minus m1 equals negative 2.50 times the logarithm, that's the base 10 logarithm, and of I2 over I1. And if you're worried about getting the right logarithm in your calculator, just make sure that you have the one that's log and not the one that's ln. Okay, so you want the one that looks exactly like this, and it will always be base 10 unless you specify otherwise. So the default, in other words, will be the one you want, as long as it says log. Okay, so what we want to actually think about here is how do we solve a logarithmic equation? All right, so how do we solve a logarithmic equation like this one, in other words? Okay, and again, wait till the end of the video for a numerical example. Here, I'm just going to talk about the approach. Okay, well, let's consider a simplified example. All right, so consider a simplified example where we're going to get rid of some of the complications such as 2 terms on the left and some of our values here as well as the fraction inside the logarithm. And we're just going to simplify it to x equals negative 5 times the logarithm of z. All right. So in other words, I just defined z as, I2 over I1 and so on. And don't worry about that too much, other than if you look at my hint right here, we actually are solving for I2 over I1 as a variable in itself. So there's no reason to split it apart. You might as well call it z and just think of it as a single unknown. All right. So as the general approach, how would we solve for this? In particular, how would we solve for z? Okay, so how do I solve for z, the thing inside the logarithm? Well, like a lot of algebraic approaches, I want to start on the outside and work my way in. So I want to divide both sides by negative 5. And so my first step is going to involve x over negative 5 equals the logarithm of z. So what I've done here is divided both sides by negative 5. So on the right-hand side, negative 5 over negative 5 is canceled, just remaining just leaving a coefficient of 1, which doesn't show up. So we just have a log of z on the right. And now my next step is to undo the logarithm by raising both sides to a power of 10. Because what a logarithm is it's the inverse function as a power, all right? Particularly a power base 10. So what that looks like is I take 10 and I raise it to the x over negative 5 power, and I also do the same thing on the right-hand side, where I'm raising 10 to the log of z power. Well, there you have it. On the right-hand side, the 10 raised to the log of z will undo each other. In other words, the 10 raising 2 and the log are inverses. They undo each other. All that's left is what's inside of the logarithm. And so our final expression will just be z equals 10 to the x over -5. And I'm just writing the exponents in parentheses, not necessary, but hopefully more clear. And I've also reflected the values across the equal sign in that very last step, just so I could have my final result, z by itself, the thing I was trying to isolate or solve for, on the left as we read from left to right. So there you go. That is how you actually solve a logarithmic equation, in particular solving for the thing inside the logarithm, which is the hardest part, and really what people mean when they say, how do you solve a logarithmic equation? All right, so that's it for part A. On to part B. Now in part B is our only other equation other than the logarithmic equation known as the apparent magnitude equation, and that is the inverse square law for light intensity. There's other versions of the inverse square law for other physical quantities, as well as some generic mathematical ones, but that's getting into the background theory, so we'll save it for another day. So the key idea here, and this is going to hold true for most of the remaining parts of the problem before I do the more in-depth numerical examples at the end, is I want to be careful about defining my 4 variables here. And what are my 4 variables? Well, I1, I2, R2, and R1. And it's not a typo. They're supposed to be, reciprocals of each other. In other words, I1 is on the top on the left, R2 is on the top on the right? So that's the way it is expressed. And the reason I want to be careful about defining them is because that's kind of half the battle here, is you want to make sure that you're not mixing anything up. So let's go ahead, and for this problem, we're going to set 2 as Earth. And think of this as my advice. Set 1 as Orcus, which is the planet that we're solving for. The world is a dwarf planet. And then we can directly solve for I1, which would be I Orcus. Okay, so thus I1 is I Orcus. Because we defined anything with a 1 refers to Orcus. Anything with a 2 refers to Earth. And so then we'll be able to directly algebraically solve for I1 with direct substitution. So then I'll just say, and then directly solve for I1, which you can read as I Orcus, but it's simpler to write just I1, right? With simple algebra. Now, we didn't have to do it that way. We could have just as easily set 2 as Orcus and 1 as Earth. And that might be tempting because you think, oh, you start at Earth and you compare everything to Earth. But as the equation is written, that means that we'd have a little bit of extra work because our only unknown, and I'm going to go ahead and highlight our single unknown here, and then I'll do the opposite and highlight the knowns. But the only unknown is I1. Well, it makes sense to have, set that as a thing that we're trying to solve for because it's easier to solve for I1 than it is to solve for I2. Not that it's that hard to solve for I2, but you can save yourself a step. All right. And to just reiterate what are our knowns, the things that we know, I Earth, which I defined as I2. So right there. All right. We also have our Earth, which would be our R2. And then our last known is our Orcus, which is R1. So then you can see the only one that's not colored is our only unknown, and simple algebra to solve for it. Plug all your values in. I have a note about how you don't have to convert in this case because it's a ratio and the units are going to cancel out anyway, so you don't have to worry about converting AU to kilometers, let alone meters, as you have to in some equations, but you don't here. Essentially, if there's no constant, you don't have to as a general rule. So here you don't, and you will naturally get the same units for I as your other expression for I. So since I Earth, our known value of I, which is intensity, right? To not just call it I, it's a value. It's essentially how bright a light is. All right, different than power because it's power spread over area, as the units imply, watts per square meter. And so when you just leave everything in those units, in other words, leave both the distances r in the same units, so they cancel. When you solve for your unknown I, it will be in the same units as your known I, your known intensity. So in other words, your final solution for I1 will be in watts per square meter. More on that with the numerical example. Actually, I solved for a ratio, the one I'll show you, but here, this would be another case of a numerical example, but not one that you'll see in this video. All right, but I'm still seeing plenty for sure. Okay, so on to part C, right, which is basically the same as part B. All right, so I'm not going to write, so I'll just say the same key idea. And that key idea being defining your your 1 and 2 carefully, making sure they match up with what you're trying to look for. In this case, we're actually trying to find I again. In this case, we're trying to find I, or the intensity of light at a different world. In this case, Haumea, which is a dwarf planet way out in the distant edges of the solar system. All right, so same key idea as B, as part B. All right, and here, I'll just lay it out for you again. We're going to set I1 as I Haumea. We're going to set I2, just as we did before, as I Earth. All right, or just basically saying that all the 1s apply to Haumea, all the 2s apply to Earth. It's really as simple as that. And then we're just going to do the exact same approach in terms of solving for I1 because we know both the R's. It would be the same value of R Earth that you had in part B, and then you're just going to plug in your essentially substitute known, which is going to be right here, and that is your known radius or distance from the sun to Haumea, 43.1, instead of what it was in part B, where it was 39.2. So not a big difference. All right, so then on to the next part, because not much to say, and certainly no more to say about part C. Moving on to part D. Now in part D, we are going to do something a little bit different. This is the first time that we're actually going to solve for an apparent magnitude. Now it's worth mentioning, again, not getting into the background theory here, that apparent magnitudes don't have units. They are a log scale. Log scales never have units. Examples of well-known log scales include the earthquake scale, the way that we talk about the strength of earthquakes, and even more well-known, the way we talk about the loudness of sound, and we use decibels. Those are both examples of logarithmic scales, which I call log scales, and they never have units because mathematically they can't. This is no different. This is just another example of a logarithmic scale, a little bit less well-known by astronomers for sure, and it's just called the apparent magnitude scale. And it's just a way to compare how bright objects are in the sky. And we can kind of take a look at that just to appreciate it, that if you look, the apparent magnitude of the sun has a value of -27. That means really bright, okay? So negative values are bright. And then we get to objects like Polaris, which are visible with the naked eye, but much dimmer, right? Not everything is much dimmer than the full sun in the sky. You can look right at it, for example, Polaris that is, or even the full moon, which has a value of about -12 for its apparent magnitude. But getting back to Polaris, it actually has a positive value of about 2. All right, so that would mean it's much dimmer. And the advantage of the logarithmic scale is we can talk about huge differences in terms of their actual intensities, which would be watts per square meter, and compare them without worrying about these big scientific notation necessary values that vary by billions or millions. Okay, so it's a way to condense the information and have numbers that we can kind of grasp easily the way our minds work and look at them and compare them directly. And by the way, maybe to drive the point home, we can get to the faintest object in the sky with an unaided eye and no light pollution, so maybe out in the desert somewhere where there's no city lights around, then you could see something that is as dim as -6. So that'd be the limit of what you could see. Once you introduce, telescopes and so on, then you can see even dimmer objects. And you can see they just get dimmer and dimmer, which means they get larger and, in the positive direction. and that's the apparent magnitude, a dimensionless value that is directly related to intensity, as of course the formula implies. So the idea here is that if you know a pair of intensities, because maybe you just happen to know both of them, or maybe you knew the distance to one of them and the intensity of the other through direct measurement, such as using a solar panel or something, and then you were able to then calculate the second intensity, as we were doing in the previous parts of the problem, for example, or at least calculate the ratio. Then you get to the point where you say, okay, well, you know those values, and then you know some apparent magnitude. The sun is a good baseline, a well-known value in terms of apparent magnitudes of negative 27. Well, then you can find the other apparent magnitude. That's the idea, right? And again, fast forward to the end or stay to the end for an example of a numerical example of this. But let's talk about the key idea first. Okay, so the key idea for D, all right, is going to be defining our ones and twos again. So we're going to, so no different than before, except we're going to kind of carry on with one last step. So think of it as sort of, starting off the same, but then carrying through. So we're going to have I2 as Earth. And that's just, again, sticking with the logic of having our math be a little bit easier. So you can see there's definitely a trend there. We keep defining, I2 as Earth, which means we're going to have I1 as Haumea. Okay, and we already, know both those values because we actually just found I1 in the previous part, in part C. And then we're going to find M1 or rather M2 is what we want to solve for. Okay, but first we're going to talk about the one other thing we're going to define, which is M2 as M Earth. Okay, and M Earth, but you don't see Earth on that figure. What do I mean? Well, I actually mean M Sun. It's the sun as seen on Earth. So we'll just write it as sun on Earth. Okay, and that is a known value. All right, so you have to look it up from the table, and what it turns out to be is that M2 is approximately negative 27. So that's we need that to be able to solve directly for our M1. Okay, and again, the logic here is that by having M1 be our unknown, which I'll write right now. So I'll say thus our single unknown value, but I'll just write it as unknown. I'll write unknown value. All right, dimensionless value, right? It's going to be apparent magnitude is M1. And since all ones are associated with Haumea, just like all twos are associated with the Earth or the sun as seen on Earth, well, that's it. That's what we're solving for. We're solving for the apparent magnitude of the sun as you would see it if you were an astronaut, standing on the surface of Haumea, this strange, spheroid-shaped or ellipsoidal-shaped planet, right? Stretched out planet, dwarf planet, that is. Okay. And then we are all good to go. All right. So then, so simply solve for M2. Now remember that the equation has M2 right out in front. So solving for M2 is fairly straightforward. And you can flip back to page 1, which is the equation you're using, but I'm just going to reference it right here. All right. So the equation is M2 minus M1 equals negative 2.5. And that's actually why there's that leading negative on the right-hand side to have the order of the unknowns or the order of the variables actually be a little bit more intuitive. I do that on purpose. If you look online, you can actually see it expressed both ways. But I think this way is easier to read. And they're both right. It's just a matter of how you're going to multiply things through. And then it's going to be I2 over I1. Okay, now I could have just as easily wrote, M Haumea minus M Earth equals negative 2.5 times the logarithm of I Haumea divided by I Earth. Okay, but I didn't because it's easier just to write twos and ones. And I think it's better than just kind of a reference here where you know that, all twos refer to Earth and all ones refer to Haumea. And so then as I was saying, the algebra is quite simple because all you need to do is just isolate M2 no, tricky thing about having to find the variable inside the logarithm. We're just trying to find a value that's sitting right out in front. And so it literally is going to be as simple as, well, I'll leave it up to you actually, but you just have to move everything to the other side and you're good to go. So you're just going to isolate this as your unknown. All right. And then you're done. That will be your value. Remember, it doesn't have units. So on to the very last part and the key idea associated with it. So part E, before I show you a couple of numerical examples. And the idea behind the numerical examples is just so you might, kind of see how the numbers work out for values other than the ones you were given. But let's take a quick look at part E before we do that. Okay, so the key idea for part E is that it's just going to be all the same stuff except for 2 steps instead of 1. All right, so similar to to C and D. All right, but combined. So it's basically just rinse and repeat all the same stuff you did for Haumea, but instead of doing it in 2 separate parts because you've got some practice, now you're just going to do it all over again, but just as a single question. And that's going to be for a different planet, one that is a little bit less known and less confirmed, for that matter, called Far Far Out. It's as far as we know, the most distant dwarf planet with no real characteristics known about it. But we're going to find both I2 and M2. Okay, so there's 2 steps in this one. It's really kind of the only problem that has 2 steps. So it would be, and that's just because it is a repeat, so that it's building on ideas that you should be familiar, at the point that you get to this last question in the homework. So the first step is to find I2, all right, and then to find M2 is the second step. Okay, well, what does the 2 refer to? Well, just as before, you want to think about, what matches up with what. So you're going to define, no surprise here, shouldn't be at least, I2 for, far, far, all right, or far, far out, but let's call it far, far, all right, and then we're going to define actually, do I want to do 2? I tend to mix them up, so I want to make sure I'm doing it correctly here. I actually want to define I1 for far, and then solve for all of my, let's see. So if I'm defining I2 as Earth, okay, yeah. It's kind of an interesting thing, right? Because the inverse square law, it's easier to say that the 1 is the thing you want to solve for because it's a little bit less work. But then with the formula as written, and this is really kind of the best way to do it, to write the apparent magnitude formula, it's better to define the 2 variable as the thing you want to find. So there's kind of pros and cons to both. So I'll go ahead and stick with the 2 for both cases. All right. So kind of the opposite logic that I applied to part B, but that's because because it combines 2 steps. It's worth sort of thinking about pros and cons and how you want to do it. There's going to be a little bit more algebra, in other words, to solve for the intensity, but it's going to be worth it because there'll be a little bit less stress and less chance of error when you solve for the apparent magnitude, which is the more complicated formula. Not that either of them is particularly complicated. Don't worry too much. All right, but we're going to define I2 for far, far, and we're going to define M2 for far, far. And the important thing here is that you just have to be consistent. So, if I'm saying that the variable 2 or the subscript 2 applies to far, far out, this dwarf planet, then that has to be, for both the intensity and the apparent magnitude. Okay, so they have to have it has to be the same variable. You can't then say that it's going to be 1. The subscript 1 is going to apply to far, far out in terms of intensity, but yet the subscript 2 is going to apply to it for apparent magnitude. That will give you the wrong answer. So you have to be consistent, and to hopefully drive that point home, then we would have I1 for the intensity of Earth, and likewise M1 for the intensity, or rather the apparent magnitude of the sun on Earth, as seen on Earth. Okay, so all ones apply to stuff related to Earth. All twos apply to things associated with the distant dwarf planet far, far out, which really is quite a bit further out than our other ones at 132 AU. Remember that the Haumei was only at 43.1. All right, so that is the idea, all of the ideas for all 5 parts of the problem. All right, so stay for a couple more minutes if you want to see some numerical examples. Now, I've been calling these the extended numerical examples, but they shouldn't take much longer. So let's go ahead and duplicate this page right here, and we're going to consider finding, a ratio of, and this is for A, all right? So we're going to, all right, not use those values, but instead we're going to find I2 over I1. I'll write that as a sentence. So we're asked for the same thing, but of course with different values. So find I2 over I1 for the Polaris compared to the full moon. So Polaris compared to full moon. And if you're thinking, well, wait, this is so different. It's comparing a star to the moon. It's not comparing the sun at different planets within the solar system. It doesn't matter. It's just comparing 2 values on the apparent magnitude scale. That's it. That's all we care about. All right. So then we would go ahead and think about what are our knowns and unknowns. Okay. Well, we just have a single unknown, which is this one right here. All right. So the ratio itself is acting like a variable, and we have 2 known values, and those would be found on the number line on the figure, which would be the apparent magnitudes of Polaris and the full moon, both seen in Earth sky, of course, because this entire figure here just refers to objects as seen in Earth sky. Right? We're extending it to think about other skies in the solar system, but the most common use and the baseline understanding of it is to think about what we see in Earth sky when we look up at night. All right, or in the case of the sun, we look up during the day. So our known values are going to be, all right, so M1 is going to be 3, and then M2 is going to be negative 12. Well, what does that mean? Which number did I assign to which object? Right? Because I said that's a big deal in terms of like making sure that you don't make mistakes on these problems. So take a minute and ask yourself, like, what is it? Which one did I assign to which? If you haven't memorized the figure with all the apparent magnitudes, you might want to flip back to page 1. But hopefully, do you see it? Well, what I've done is I've just said that 1 is for Polaris and 2 is for the full moon, because of course the apparent magnitude of the full moon is negative 12, because negative numbers mean brighter. I know it's kind of counterintuitive, but it's common with logarithmic scales to have that sort of result. And that means that we're good to go. And all we have to do is isolate our ratio. So let's think about the math. I won't go over it again, the general math, because I did that with the x and z values when I first talked about this problem and its key ideas. So I'm going to jump right to the solution after we have isolated them. So it's going to be I2 over I1, where of course that was the same as, and I will write this down just in case you got confused with your variables, I moon over I Polaris. Okay, so just equivalent statements. And then so once I've done all the math to solve for that ratio of intensities that used to be within the logarithm, I would have 10 raised to the power of, and then it's just going to be M2 minus M1, all right, divided by negative 2.5. Now I could have distribute that negative instead of having it in the denominator. So then it could have been M1 minus M2 divided by positive 2.5, but that's not really necessary, right? So then just to go and plug in the actual numbers and show you the answer, I then would have, I'm going to rewrite this because it was so shaky and choppy because I was running too small. So let's do this one more time. So it'd be M2 minus M1 divided by negative 2.5. And that negative 2.5 is just a, it's a constant that just refers to this particular scale set for apparent magnitudes. Different apparent magnitudes have essentially different coefficients in front of the logarithm. That would be true for like earthquakes and decibels that I mentioned before. So that it's just a particular for this scale. That's all. And it'll always be negative 2.5. So then plugging in the actual values, as I said, up top, we would have negative 12 minus positive 3, so that would just become negative 15, divided by negative 2.5. So that means that the actual exponent will be positive because negative 15 divided by negative 2.5. Well, that's like something like probably 8 or something. So it's going to be like 10. It actually ends up being exactly 6. So I'm doing my estimate, not completely accurately, but it's to be exactly 10 to the 6, which is just a million. So in other words, Polaris is a million times brighter in terms of watts per square meter actual intensity than the full moon. And that really highlights the advantage of the logarithmic scale because comparing 3 and negative 12 is a lot more intuitive than comparing 1 and a million. How do you make sense of that when you say it's a million times brighter, right? How would you graph it? Well, the logarithmic scale takes care of that. Okay? But in reality, it's much, much brighter. All right, so and that's the downside of logarithmic scales. They can kind of hide how what actually is the huge difference between these values. But hopefully the advantages outweigh the disadvantages. And our very last thing we'll do in this video is go ahead and do a numerical example for part D. And that's because I wanted to show an example of actually solving for an apparent magnitude to just hopefully drive home the fact that they don't have units and so on. All right. And by the way, there's also no units in this case because it was a ratio. So it would just be 10 to the 6th. I wouldn't put any units on it. So a lot of your answers won't have units, but do pay attention to the few that will, which are any of the times that you're using the inverse square law on its own to just solve for intensity. All right. So let's wrap it up. So here we're going to, all right. So, same approach, but not those values. That's why I cross it out. And so instead, we're going to use, all right, we're going to, instead use a intensity. So imagine that, maybe you did some sort of similar approach where you knew some distances, or maybe you're just given intensity. So we're going to use an intensity of I2 equals 10 watts per square meter, all right, and a comparable intensity on Earth of I1 equals 1370 watts per square meter. And if that number looks familiar, that's because that is actually the same number for the intensity of the sun on Earth on average, which is 1370 watts per square meter. And that's a kind of a great comparison because then we immediately know what the apparent magnitude of the sun is. It's the value of, flip back a couple more pages, negative 27 right there. So that means that our last known for this numerical example is none other than M1 being negative 27. And then that means that our unknown that we want to solve for, so unknown to find, is, you guessed it, M2. All right? So then how would we go about solving M2? Well, here I'll go ahead and show the approach, which before I guess I was trying cagey and not tell you exactly how to do the algebra, but here you go ahead and see it, that once you go and look at the apparent magnitude formula, that big formula on page 1, and you just isolate that M2, the thing right on the front on the left as you read from left to right, well, of course, it just becomes M2 equals M1 minus 2.5 times log of I2 over I1. All right, so then if we plug everything in, and so this is already having done the math. If you're wondering why it looks different than the formula, that's because, I'm doing it for you, but hopefully it's obvious how that worked out. And then, like I said, plugging in the numbers, we'll plug our known value from the figure, from that number line, negative 27, minus 2.5 times the logarithm of 10 over 1370. Yes, those both have units. So, watts per square meter, watts per square meter. Finish my, division there, dividing line, 10. But of course, the units just cancel. So it's just numbers over numbers. And that's important actually because, using physical equations, you can never have anything with units inside logarithms, just like you can never have anything with units in exponents that wouldn't make physical sense. And so it always has to be ratios in some form or another. And this is no exception. And once you plug everything in, and I ran out of space, so I'll go right down to the line to here. Once you plug everything in, you find that M2 is negative 21.7. And if you're thinking that can't be right, that's still, a very, large number in the sense that it's close to negative 27. And that means that it's even brighter than the full moon. Well, actually, it totally is right. And it just goes to show that having what seems like a really small, intensity in terms of actual units of watts per square meter, 10, as compared to, 1,370, doesn't make a big difference with the apparent magnitude because it's a logarithmic scale, right? So that means when we're talking about things, that have, values that are, not negative 20, but, 0 even, or 1 or 2 in the case of Polaris, or Polaris was 3, well, think about what they would be in watts per square meter. It'd have to be some tiny decimal. In fact, it'd be, moving the decimal over 6 places, which is what it meant when we got that 10 to the 6. And that was comparing it to the full moon, not comparing it to the sun. What would happen if you compared the full moon to the sun? What would you expect? Well, food for thought. Okay, so I hope all parts of this video have been helpful. Thank you so much for watching.